Okay, if we can go ahead and get started, please. Today, we're going to talk about process capability analysis, where this fits in the overall course. We're in the DMAIC, and we want to measure the current state. And we can use the yield or ppm if we have continuous data. What we're going to do today is talk about another way. So there is another way to do that. And the another way is to use indices. So rather than talk about in terms of parts per million defective, we're going to convert them to an index. This index has some different uses in industry. In industry, people use this for part approval. So there are many companies, in particular those in, say, the automotive industry or aerospace industry. They have what's called the production part approval process, or PPAP. And what that approval process requires is it requires people to meet some quality threshold. Instead of saying, I want you to be at 99.997% quality, they give you an index number. This index number is going to be equivalent to some quality performance, but it's another way people use that. Another reason why people use indices is it can help with part diagnostics. In particular, it gives us a way to evaluate, do we have a mean problem? Do we have special cause mean shifts? Do we have high common cause? To help us put our process into one of those groups, we can do what are called process capability indices. It's actually kind of a challenging topic for many people to see it for the first time. So you have to pay close attention and you have to have some practice, but it takes a while to kind of get it all kind of organized. The basic idea, though, is I want to make comparisons. For example, if I look at the picture there, I want to look at this picture and I want to be able to say, okay, well, how does the variation compare to the spec limits? In this case that I'm showing you here, the variation of the process is really much less than the specification width, right? That's a good thing. Even if the mean drifted a little bit, so if I look at X bar and I moved a little bit, I'd probably still be fine on being in specification. I want to have a way to help me distinguish between how good I'm doing in terms of variation, also how good am I doing in terms of both mean and variation. And we're going to use capability indices to help us do that. Again, though, part approval and diagnostics are two things that we pick up. If we just use the yield number by itself, we could do that for a part approval, but sometimes when we have a low yield, it's not clear whether or not we're worried about our mean being off target or our variation being a concern. So we want to have a little bit more detail to do that. For this lecture, which would be a standard way to apply this, you would have some part or process, and from that process, you would have some y's. Maybe you only have one, maybe you have several. Suppose you're measuring a part as an example, and you have 10 y's. What you want to be able to do is you want to be able to quickly summarize the performance of all 10 of these and help you diagnose what it is you're trying to do. In this particular example, we're measuring a part in terms of its distance and diameter and depth. And we're going to measure everything relative to a nominal design. I bring this up because lots of us will measure an industry and people will say, measure relative to the nominal. So if the length is supposed to be 4 feet, everything gets measured relative to that standard, and you end up with a target or nominal value of 0 with a plus or minus. This is a nice way to do things because oftentimes we don't really care what the exact measurement is. We just want to know whether or not it is at the desired value. Now, as I mentioned, what we're trying to help us do is to do some problem solving. Let's say we went out and we got 12 subgroups of size 3. We got a total of n equals 26. If we were to plot this, each dot being 1 through 36, we could also look at some things. For example, this area right here is an area where we're looking to see probably some common cause variation. We're getting some up and down, just probably due to the inherent variability of the process. It does look like at some point the mean of the process has shifted. In this case, we want to be able to identify that we have a mean shift. And then it's also worth pointing out that this green line, the target value was 0. So the long-term mean is 0.6 millimeters away from the target value. So what we have here is we have a process where we have some common cause, we have some mean shifts, we have some mean deviation from nominal, and we're trying to understand what is the impact of each of these, which is the biggest one to go worry about. And we're going to use our indices to help us quantify these effects. Right? We can just certainly look at the data and say, you know what, we want to get rid of the mean shifts. We want to be able to quantify them. How are we doing so far? We okay? All right, to help us quantify, we're going to talk about process capability indices. I'm going to expect you to know 4 major indices: CP, CPK, PP, and PPK. If you work in certain industries, you would have probably been exposed to these, but if not, there are a lot of industries that use these. And you will also notice when we've been doing our process capability analysis tool inside of Minitab, this is part of the output. And we want to make sure we understand all of the output provided to us for that tool in which we've been using. I will expect you to know how to distinguish between all 4 of these. We'll also talk about the case where we have just a one-sided specification. We can't do certain indices when that happens. Then we want to talk about the relationship between the capability index and ppm defective. These are linked together. Then one of the reasons we do this is we ultimately are trying to figure out how much am I trying to improve? How much do I have to shift the mean? How much am I trying to reduce the variation? Once we have the index, it is easier for us to answer this question. And this is a common question. You tell someone that you're not meeting their goals, you got to go shift the mean. They're going to say, how much? You tell someone to reduce the variation, they're going to say, how much? We want to have a tool to help us with that. Pardon me. The last thing we're going to talk about is what do I do if the data is non-normal? We mentioned before we can always just use the observed ppm. But we're going to talk today about an additional way in which we can do that. All right, when we talk about process capability, definition-wise, we're basically trying to figure out how well our output meets specification. Again, stability is control SPC. Capability goes with specification limits. Up until now, we've been using ppm or yield. Today, we're going to add some additional capability indices. And there are others beyond this, but these are the big 4. And once you learn the big 4, the other ones are just, other calculation methods. A good question is why? If we think about the case of a 2-sided specification, there are 4 pictures up here. You could start out and you are in the worst case where you have high variation and off target. How would I say, or why am I saying you have high variation? What is the visual clue that you have high variation here? What is the visual clue that you have high variation here? Yes?
Curve goes all the way from the power cell to the US cell.
Okay. I would say that the width of this curve is much bigger than the spec limit width. Everybody see that? I also say that the off target. How do I know the mean is off target? If I calculate the mean of that normal distribution, it's deviating from the target value. In this one over here, I say high variation on target. I say on target because the mean is at the target value, which is a good thing, but I'm going to get defects here because the width of that distribution is bigger than the tolerance. Sometimes I am in the picture over here. I have a mean off target, but I'd actually argue I have low variation. I have low variation because if I took that same level of variability and I shifted this curve, I would not have any problems. I would be in specification. These are all possible conditions. I want to know that. If I have this situation, I might think about how might I solve that. A classic way to solve a process with too much variation might be to do what? Maybe change the standardized work. Try to get more consistent process. If I have a problem which is low variation but mean off target, maybe that's just a matter of a setting. Maybe some setting in my process is off. Or maybe I have to add a person to do this job to be able to increase the time, or take a person out depending on which direction I am moving. But the idea is I want to have different indices to try to help me see different conditions to help me with problem solving. This is the link between our indices and diagnostics. Questions so far? All right, hopefully that gives us a backdrop. Again, we're going to use 4 indices, CP, PP, CPK, and PPK. I will note that there are indices out there. People will use CR, which is just the 1 over CP, or PR, which is 1 over PP. These are just inverses. We'll focus in on the top 4. All right, I'm going to definitely ask you questions to distinguish them because it's about diagnostics. So we got to think about what is it that I have to understand to identify which indice goes where. The first question is whether I want to include or exclude the mean. If I want to exclude the mean, there is no K in the index. CP and PP formulas have no mean involved. And you might say, why would I want to do that? Well, sometimes I want to look at the process just based on variation, and I want to ignore where the mean's at. I want to understand where I'm at just in terms of the variation or the potential. All right? When I exclude the mean, I'll get CP and PP, and these are really about the potential due to variation only. When I want to include the mean, I will use CPK and PPK. So if you see that letter K, that is implying that you're including the mean in your index calculation. All right, that's one distinguishing factor. The second distinguishing factor is which sigma do I use in my formula? I've got 2 options. There is sigma within a subgroup. For example, I did SPC in a range chart, and I estimate sigma within a subgroup as R bar over D2. Or if it's a moving range, MR bar over D2 is the best I can do. That was the within subgroup variation. That's different than the overall standard deviation. If you just were to go to Excel and do equals STDEV and the sample standard deviation, that's the overall. Now, what separates them? If I have mean shifts in the process, these numbers will be different. For that reason, I can use them for diagnostic purposes. The ones with the letter C You can think about those as the common cause standard deviation, or the R bar over D2s, and then the PP and the PPK using the overall standard deviation. Let's do these in a little bit further. Common cause is the same as inherent, is the same as within subgroup. If I do SPC and I have an in-control process, I can use R bar over D2, I can use MR bar over D2, or I can use what's the pooled standard deviation. If you took a stats class before, you should have been exposed to analysis of variance. And one of the things you get out of analysis of variance is you get the square root of the mean squared error term is an estimate of sigma pooled. This sigma pooled is the same thing as an estimate of inherent. After accounting for the mean differences, that's the inherent variation of the process. All of these pooled R bar over D2, again, they're trying to come up with what is the within or common cause. If I want to use the sample standard deviation, that's going to go into the PP and PPK. Excel is just the equals STDEV, or this is the formula you could pull out of any textbook in the world to calculate the standard deviation. All right, here is very important to start to see this. If you have a process and everything is in control and there are no special causes, what should be the relationship between the overall and the within group? If both the range and X bar charts are in control and there are no special causes, what should be the relationship between sigma within group and overall? Same. They should be the same. Will they be exactly the same? Unfortunately, you have two different ways of calculating the same thing. The numbers are going to be different. But if there are no special causes, they should be similar, right? They're just two different ways to estimate. If you start to get special causes, what's going to happen between sigma overall and sigma within? If you start to get a lot of special causes and your mean starts to walk around, what will you get as a relationship? Sigma overall will be bigger or smaller than sigma within. If the mean is walking around, these are all different subgroups, then your sigma overall is going to start to become greater than your sigma within. Everybody see that? You got to kind of get this, right? When you make an SPC chart and you get special causes and the X bar chart starts to move around, that means that your overall variation is bigger than what you would get as the inherent. If you can eliminate all of these causes and everything was like that, then eventually overall and within should be similar. This is why it's a diagnostic tool. Questions so far? If no special causes, you should get, and I should really do this, about the same as PPK, and CP will be about the same as PP. They won't be identical because it's different methods of estimating, but they should be close. Are we moving on? All right, let's now move to the formulas. Again, CP is going to use the within subgroup. PP is going to use the overall. When we include the mean, we will use CP and PPK, CPK and PPK. One more thing, CP and PP, you can only use these if you have a bilateral tolerance. Bilateral tolerance is when you have a plus or minus t. If you have a USL only, or an LSL only, then you can only get PPK and CPK. I'll show you that with the formulas, but the CP and PP is excluding the mean, but can only work if you have a bilateral tolerance. All right, let's do a couple of pictures and some formulas. Let's look at this formula right here. CP is the relationship between the tolerance width, USL minus LSL, divided by 6 sigma. Now, I could have different things going on. I could have a picture that looks like this, and that would be a picture of a CP of 2. Now, if you want to think about what does it mean, if you look at that formula, specification divided by 6 sigma, a CP of 2 means I could take and fit 2 6 sigma distributions inside my tolerances. I could fit 2 distributions inside. That's kind of what you can think about that as. Or you can take the reverse, do 1 over 2, and say 50% of my tolerance width is being used by 6 times the standard deviation. But if you look at the formula for CP, is there any indication of the mean? Nothing. Therefore, I could also have this picture. This could be a CP of 2. Now, in this case, I'm getting a lot of out-of-specification conditions. However, if I could shift the mean, this process has low variation. Again, CP is giving me a measure of whether or not I have low variation or not. And it's taken the mean out of the equation because it's assuming that, well, I'm going to treat the mean separately, and if I could shift it, how good could I get? By the way, if you had a CP of 1, you'd have something like this. 6 times the standard deviation will be basically equal to the USL minus the LSL. This could be a CP of 1 as an example. So I want CP numbers to be large or small? 2 is fantastic. Above 2 can be unlikely. It can happen, but 2 is fantastic. If you can fit 2 distributions inside your specification width, you have low variation. Even at 1, you're at a 99.73% quality level if your mean equals target. If your mean equals target. But if you can get that CP number to be higher, that obviously is better. Now, where do I get sigma from? If it's a CP formula, I either use R bar over D2, MR bar over D2 if it's an IMR chart, or if I use ANOVA, I use the sigma pooled. If you remember from a statistics class, that's the square root of the mean squared error. You remember that at all, or kind of, maybe? All right. We'll let software make these calculations for us. When I do PP, the only thing I'm going to do is I'm going to take and I'm going to divide by 6 times the sample standard deviation. Instead of using the sigma within, I'm going to use the sample standard deviation, which in Minitab is going to be called the sigma overall. Now, we've been doing this already. We've been making the process capability normal analysis, and you've been getting the observed and the expected PPM. There's also the CP-PP, and there's been an aside that said standard deviation within, standard deviation overall. I'll show you that coming up, but now we start to show where these are used. How are we doing? We all right? Now, I want to take into account the mean. When I want to take into account the mean, I'm going to do a CPK formula. Go through that first. CPK formula is going to be the minimum of the CPK lower and the CPK upper. CPK upper is relative to the upper spec limit. CPK lower is relative to the lower spec limit. I compute both of these numbers, take the minimum value, and that becomes my CPK. I notice that sigma can be used as R bar over D2, MR bar, or pooled. If I use PPK, sigma is estimated using what? Sample standard deviation. By the way, in order to do that formula, I pretty much know whatever side the mean is closest to the spec limit will be the minimum value. In other words, if the mean value is closer to the upper spec limit, I will get a CPK upper. If the mean's close to the lower spec limit, it'll be the CPK lower calculation. I can do them both, but I can use logic to figure out which one's going to be the minimum. Interesting thing here. Can CPK be negative number? Can CPK be a negative number? Yes? Absolutely. Anytime your mean is outside the specification limit, you get a negative CPK or a negative PPK. Can CP or PP be negative? Yes, variation has to be greater than 0. So CP, PP will be positive numbers. CPK and PPK could be negative. If CPK or PPK equals 0, that just means you have a mean equal to a specification limit. Do we want higher or lower numbers of CPK and PPK? Higher or lower numbers? Want large numbers. Right. Doing okay? All right, these are the calculations. Industry for buy-off or approval processes often has the following requirements. CP or PP, they want to be greater than 1.67, or CPK or PPK to be greater than 1.33. Some people might use CPK or PPK to be greater than 1.67. These are standard guidelines. If you want to be at a Six Sigma level, the 3.4 per million, you would express these as you want a CP to be greater than or equal to 2, and you want a CPK to be greater than or equal to 1.5. CPK of 1.5, if I went to a normal distribution table, that's the same as 3.4 per million if I have that level of CP. I'll explain this in a later segment on where does the sigma level index come from. But for now, these are the typical industry guidelines that we use to define our quality levels. By the way, you may go some places that will say, before I report, so before you report an indice, you need to make sure that the process is in control and normally distributed. If you are going to do that, then there is really no difference between CP and PP and CPK and PPK, right? Because the process is normal and in statistical control, that means there's no special causes. And therefore, sigma overall should be roughly the same as sigma within. I'll say this again. If you're going to say, in order for you to report your indices, you must demonstrate normal and in control, then these indices should be basically the same. The calculations are slightly different because of different formulas. In that case, people would say report CP and CPK. Another way to look at this is to think about PP and PPK more for diagnostic purposes. We're going to use PP and PPK more for diagnostic purposes in this class. Are we okay? You have to go to an industry and see what their requirements are. I'm just giving you general guidance. All right, let's think about these as what do they look like based on their numbers. Let's say we took data. In this case, we have dimension 3, and we went and we made the following. In this case, we have observed ppm of 0, and our expected ppm is also quite low. We're still assuming that that distribution crosses over if I filled in a normal curve. This is the report we've been making for the measure phase. A couple things to notice in this report. Minitab gives us standard deviation overall and standard deviation within. In order to get standard deviation overall, it used what method? Sample standard deviation. In order to get the within, it's going to ask you what estimation method. And there was a button we've been pressing before. You could have clicked R bar. You could pick pooled. There's different ways you could pick it. I will try to tell you on homework problems, pick this method. Not that I really care. They're just different ways of estimating the same thing. But just to be consistent with solutions, I will say pick this method. In this example, is there a big difference between the sigma overall versus sigma within? .096, 089. Not a real big difference. In fact, if I did a SPC chart, pretty good chance that this process is in control. Not a big difference. Then if we look at the indices, the PP index is 3.45 and the CP index is 3.74. Now you might think of these as a big difference, but both of these are way above 2. And in this case, when I say a big difference, I'm usually talking about at least a 0.5 different in the index. I don't even like to give out those rules because then people use them as their gospel. They're always that way. A little bit of interpretation here. But when I have a very high number and their gap is not 0.5 apart in the index, pretty similar. Now, I could be fancier and I could do a 2-sample hypothesis test and do an F test to compare or something like that. But, or I can use SPC to show there is no special causes. But basically, we have things very similar. All right? Now, in this case, even though these numbers are similar, if I look at CPK, the number is 0.75, and PPK, the number is 0.69. The gap between PPK versus PP is small or wide? Really wide, right? And the gap between CPK and CP is also really wide. And you can see that pictorially. This is clearly a mean off-target problem because we're failing CPK and PPK versus, say, 1.33 standard. However, I have low variation. I have not a big difference between overall and within, and both of these indices are way above 2, or way above my threshold. We all right? Instead of me giving you a picture, I could just say, you know what? CPK is 0.5 and CP is 2.2. And I could tell you that the process is in statistical control. If I did that, you'd basically say I have a mean problem. I've got low variation, I'm in control, but I have a mean deviating, which is why I'm not meeting my threshold. Questions for me? All right, let's make another picture. Let's look at dimension 7. There is our histogram. Sigma within is 0.189. Sigma overall is 0.412. PP is 81. CP is 1.76. What's going on here? CP is above 133, 167. It's pretty good. PP is not. PP is not above, probably because of special causes. When you see a gap between them, you have special causes. Even if I just look at that histogram, what do I observe? What do we call this? Bimodal. If you have a bimodal distribution, we expect to have some special cause explaining the bimodal distribution. If you were to make an X bar chart, would you expect it to be in or out of control? For this example. If you made an X bar chart, would you expect it to be in or out of control? What do you think? You want to say the question? Have special causes. Yes.
Out of control.
Out of control. Because?
Special causes.
Special causes is making a mean walk around. That should appear as out of control. Up until now, we've been using the capability analysis. There is also what's called the capability six-pack. Capability six-pack is going to show us the overall normality, in this case non-normal, it's bimodal. It's showing us the histogram, and it's showing us the X-bar range chart. Are we surprised the range chart is in control? No. CP is high. We have low common cause variation. It's not surprising, not to do it, of course, to see that the range chart is in control. Common cause variation is low and stable. The mean is walking around, which is why sigma overall is much larger than sigma within. I'm doing a double greater than sign as a way to say much larger. Again, I'm making a, not totally subjective, but I'm making a kind of an interpretation based on the numbers and the picture. Question?
So just to clarify, when you look at the R chart, we can see common cause variation, and you look at the X bar chart, we're going to see one special cause.
Common cause for yes. Range chart would be common cause. X bar chart, we would look at that as both common and special, in the sense that the mean could be moving around, but if they're out of control, it would be special causes. So really the terms, this gets a little tricky, I guess. I'll rephrase that. Special cause is when the process changes, whether it's an X bar or a range chart. But a range chart is a measure of common cause variation. I'll make a distinction between common cause variation and the word common cause. A range chart is a measure of common cause variation. The word common and special cause can apply to any chart as either I'm in or out of control. All right, we moving on? I want to remind you that capability is not the same as stability. If I had an individual chart, subgroup sizes of 1, right, I could have a process which is stable or in control. However, it could be out of specification. You see that? You could be in control but out of specification. I could be out of control but I could be in specification. This is the USL. In fact, I can be all 4 of these. Again, I'm using individual values, not means. But I can be all 4 of these. I can be out of control and out of specification. I can be in control and in specification. Right? All 4 of these are a possibility. We are going to take any problem in the measure phase and we're going to ask ourselves, is the process stable? Is it capable? And we're going to treat these separate. Discussed this before in SPC, just bringing it up again because I care that we get this difference. All right. Some people who are working in industry have seen these indices used a lot, and they may even have bosses or quality people that tell them that CP and CPK are short-term capability and PP and PPK are long-term capability. Or they may work for companies that tell them PP and PPK are short-term and CP and CPK are long-term. In both cases, they are misinformed, all right? The difference between CP, CPK, and PP, PPK is the standard deviation used to estimate them. The idea of short-term and long-term would be based on how you collect data. If I measured 30 parts in a row, that's a measure of short-term. If I measure data spread out over time, that would be a measure of long-term, right? The difference between these indices is related to how they are using standard deviation. Now, with that said, if someone took 30 in a row and they calculated using the overall sample standard deviation, they may call that PP and PPK and the short term. They're calling it the short term appropriately because of the way they collected data. They collected data 30 in a row as a measure of the short term. In this class, or I should say one more thing, you might pull up a textbook, and a textbook might say that you should only ever do this if you can demonstrate the process is normal and in statistical control. And if you believe that, there is no such thing as PP and PPK because they're just going to be a same thing. I will do all of these because I'm doing these for diagnostics. I am making a distinction, letting Minitab make all 4 calculations, but we're doing these for diagnostics. If you were to ask me, what is your long-term capability, I would only answer that question if you could demonstrate your process was in statistical control. If you ask me what the long-term capability is, I would have to demonstrate it's in control. Just like before, when the X-bar chart was out of control, I said, what mean would you predict? And we said, I do not predict means of out-of-control processes. This isn't a real big deal to me, but because many people in the industry are kind of taught this wrong, and sometimes their boss says it and they're afraid to challenge them, and that's fine. Don't challenge your boss in a meeting, I get that. But we have misconceptions out there. Questions? All right, I'm going to move on. Sometimes we have a one-sided specification. If you have a one-sided specification, there is no USL minus LSL. In that case, we are just going to either calculate PPK or CPK. And our formula is going to depend on whether or not we have a USL or an LSL. Now, one-sided improvement's a little trickier. If this is your current state, and you currently have a PPK of 0.67, which, by the way, equivalents to a yield of 97.7, and you want to get to a 1.33, you got really two options. You can try to keep the same standard deviation and shift the mean, or you can try to reduce the standard deviation and leave the mean where it's at. Both of these would be options. What you have to do sometimes is try to figure out which of those would be easier. Sometimes shifting the mean may be easier. Other times maybe you can reduce the variation. Sometimes it's a combination of both. When we only have one specification, it's harder for us to tell mean or variation problem. Okay? I want to talk about the link between the indices and the expected PPM. PPK and CPK numbers are going to be linked to the expected PPM. The way this would work is that we're going to use software to identify a distribution, and then from that distribution we're going to calculate the probability of a defect, multiply this by 1,000,000 to get PPM. So if I had a probability of a defect was 0.0027, times that by 1,000,000, I get 2,700. Now I'm going to let software do this, but we should be appreciative of the approach. If data are normal, we should remember from a statistics class that if data is normal, I can take a z-score and convert that to a probability. You remember that? You had z-scores for a normal distribution. The z-score is x minus mu over sigma. X is either the USL or the LSL. The mean is either the x bar or x double bar, depending on what chart. And then sigma gets a little tricky because I could either use the sample standard deviation or I could use the sigma within number. As a reminder, in order to get a z value, if I wanted to look at the probability that I had some unit below my lower spec limit, I would calculate a z-score using LSL minus mu over sigma. If I wanted to calculate the probability of being above the upper spec limit, I'm going to do that based on a z upper spec limit. I can do this in Excel using the norms dist function and z values, or I can do this in Minitab. It is doing this kind of quickly because this is something that we should do a basic understanding of what Minitab is doing. For instance, if you went out and you have a mean of 12, a standard deviation of 3, and an LSL of 9 and 15. In order to do that, you would say, well, the z of the lower spec limit is x minus mu over sigma, which means it's going to be 9 minus 12 over 3, correct? So z LSL will be equal to what number? -1. And then z USL is going to be 15 minus 12 over 3, or a +1. Are you with me? Remember this from before? You had lower and upper spectrum, just the x. I used the mean and the standard deviation to come up with a z value. Once you have a z value, I can look at a table. And this table is intended to make your life a little bit easier. If I look at z of -1, I get a 158,655 ppm. If I look at above z of 1, I get 158,655. By the way, if z equals -3, I get 1350, and z equals +3, I also get 1350. Add up 1350 and 1350, I get 2700. So if my specifications are plus or minus 3 sigma in distance, I'll get z values of +3 and -3, and I'll get 99.73% in spec, 0.27% out of spec, or 2700. You should be able to take spec limits, means, and standard deviations, calculate a z value, and look at the table. By the way, you may notice, which we'll discuss later, that there is an interesting number on that table. The 3.4 parts per million, which is the, quote, sigma level, goes with a z value of 4.5. I'll come back to that later, what that means, but that's what that 3.4 is not just made up. It's a number that comes from this z value. All right, to do this in Minitab, we've used this before, stat, quality tools, capability analysis, normal. Let's say we put in our subgroup size of 3, and we tell it to go ahead. A couple things we will notice. The observed ppm, that's just what we observed out of spec. Then we have expected overall and expected within. What do you think is the difference between those two? Expected overall is going to be a z distribution, x minus mu over sigma, but what sigma is it going to use? Overall. And expected within is going to use which sigma? Sigma within. These overall and within are just coming down there. I really don't like this because it can be really not very representative of what's going on. It's an output Minitab gives because it's using the different values there. Now, in this case, maybe the numbers aren't real far apart, but up until now, I probably would have used observed because these data are not normal, but these are the results that I get. Here's my capability results, again, overall and within. We doing okay? It's just the output from Minitab. All right, this next slide I'm not going to go through, but if you wanted to take this exact same information and do this in Excel, that would be the calculations to do that. Just showing you how those numbers were done. We're going to use Minitab for this. So you should know what a z-score is. How to look up a normal probability table as well. All right, are we okay? To summarize, I give you a data point, a dimension. You should be able to calculate the process capability analysis, understand within, overall, PPK, CP, these various things that are the output. As I mentioned at the beginning of class, it's one thing to calculate some index, and we can use that for, is it good or bad, pass, fail. That's one thing that we can do for it. If I don't pass, another interesting question is, well, if I'm not acceptable, what do I got to improve? The mean or the standard deviation, and by how much? And we're going to use these indices and their whatever quality standard your company sets to help us come up with these estimates. This is a very useful thing to do. When you tell someone your CPK is 0.25, they want to know, well, what do I got to do to get better? And you want to be able to say, here's what you need to do. All right, let's do an example. In this case, let's say we're keeping track of our daily throughput, number of units produced each day. Different example. And let's say the company has set a quality goal of 1.33. .33 is pretty good quality. It's 99.997%. A little bit of potential rounding, whatever, but it's very high quality. It's not 1.5 would be 99.99966% or 3.4 per million. 1.33 is a classic number people use. You could put 1.5 if you wanted to, but classic number people use is 1.33. That's around 99.997% good. All right, we okay so far? You go out and we use the six-pack tool. In this case, we only have a single value each day, so we're going to use an IMR chart. What do we conclude from our IMR chart? Stable or not stable? That's stable, and that is stable. I have a consistent process. This is a good finding. From this consistent process, I can now estimate a value for the mean and the standard deviation. Let's say I use the center line of my individual chart, which would be a mean of 32. And then for my standard deviation, because I have an in-control process, let's say I use the R bar over D2 or the MR bar over D2, and I estimate my standard deviation as 2.71. Now, I'm not going to make a big deal about whether you round to 2.7 or not. This is trying to come up with a general number, not so exact. This is all good. The last piece of useful information is this process is normally distributed. I have a normally distributed process. I can get that by looking at this p-value here, where all these points are inside those red boundaries. Even if I had a slight departure, I'm probably okay. If I had a significant departure, I may think twice, but a slight departure is probably going to be fine. All right, we get the backdrop? The question is going to be asked of you, how much mean and or standard deviation need to be modified? To answer that question, I'm going to use CPK. In this formula, in this case, which of those am I going to use? CPK upper or CPK lower formula? I want to make sure that my throughput is at least 30 units per day. There's no penalty for making a lot of units. Therefore, I have an LSL, and I'm going to use the CPKL equation. All right, is that okay? CPK, mu minus the LSL over 3 sigma. Now, there's two ways you can do this. You can assume a sigma, solve for the mean, or the reverse. You can give a mean, solve for sigma. If I do the first one, where I say give me a standard deviation, I am rewriting my equation to be mean equals the LSL plus 3 sigma times my CPK goal. My CPK goal in this case was 1.33. If I do that, I end up with a 40.8. By the way, if I look at this equation, 3 CPK goal times sigma, and CPK is 1.33, what you really want is you want a distance of 4 sigma between your mean and your spec limit. And I probably should have drawn that the other way. LSL mean. I want a distance of 4 sigma between my mean and my spec limit. 3 sigma would only be at 99.865% good. I want to be higher. When I do that, I get a 40.8. Yes? If I take, my equation is 3 times the CPK goal. I could, but if I want a CPK 1.33 threshold, this is equivalent to saying I want 4 sigma. If I had a CPK threshold of 1.5, then I would need 1.5 times 3 would be 4.5 sigmas. So to get a CPK of 1.5, I would need a distance of 4.5 sigma between my mean and my spec limit. This is important. What I'm trying to do here is say I'm going to always have variation. I want my variation in my tail of distribution to come down and still be in spec. If I go to the bottom equation, I'd say, okay, well, if I told you the mean was 32, and I want you to solve for sigma, I would say, well, I would need a sigma level of 0.5. So now the question becomes, which of those is realistic? Do you think it's realistic to go from a sigma level of 2.71 all the way down to 0.5 given that control chart? Well, if you already have an in-control process, you're talking about taking a standard deviation. That's a big drop. How about the mean? It says I want the mean to get to what number? $40.8. That's an individual chart. Does it seem realistic to get my mean at 40.8? What's the best I've ever done? It's an individual chart. It's the best I've ever done. Best I've ever done is like 38 or 39 units. And I'm going to tell you I need to get the average above the best I've ever done. Probably not realistic. In this example, you probably need both. Now, some of you may be saying, well, how do we do that in a test? All right? Not really a test question, right? It's a concept question that's helpful, though. It's not a test question because it's some subjectivity involved here. But if you're in an actual condition, you can use these two formulas in your quality goal to give you an idea of where you're trying to get to. And you can ask yourself, is that practically reasonable? If I would have calculated this and I could get the standard deviation down to, say, 1, maybe that mean could be not such a big deal to move. But I have to kind of consider these. But the nice thing I'm doing here is I'm giving you a way to figure out where I'm trying to get to. And then I have to ask myself, is it feasible? This appears to be a mean and variation problem. I need to both shift the mean and reduce the variation likely. Questions? The reason why today's lecture starts to get hard for people is I am bringing the concepts together. I am integrating the SPC, the capability, the desired quality levels together. That is challenging. You got to think these things about how these are all connected. That when I have special causes, that results in, say, PPK being much different than CPK. Start to see how these topics connect together. Take some effort, but that's what we're trying to see these links. Questions for me? Last topic of today is, let's say our data are not normal. And we're going to use a different example. And this is based on a project that was related to resolution time for IT tickets. You have a company, they have a ticketing process when people have complaints, and they have certain types of complaints that are already categorized, and they have an initial analysis, and they get the following. Again, this is not every IT ticket, it's just for a certain type that this was done for. And we could go through this, and we could look at this distribution, and I could do a graphical summary. This is the graphical summary tool, or any tool in Minitab that gives me the normality test. And in this case, my normality test has a 0.01 p-value, which is less than 0.05, and I'm going to conclude the data are not normal. First of all, are we surprised that a resolution time is not normal? It's very common, right? A lot of things can be resolved quickly. Some problems are more complicated. You tend to get skewed to the right. Resolution time on a call center tends to be skewed to the right. It's not surprising. Now, if I wanted to do a capability analysis, I could run this as process capability normal, but just hit the observed ppm and disregard the expected. The data is not fit by a normal. Alternatively, I could try to fit another distribution. In this class, I'm going to limit us to the following 3 other distributions: a Weibull, a log normal, and an exponential. The reason I'm doing that is these distributions tend to fit skewed right, skewed left distributions. If the data is multimodal, I can search and search and search. I am not going to find a good distribution fit. That's because it's basically a normal under certain conditions. Group A, Group B, Group C. So multimodal distributions, you can search and search and search. You're not going to find a good fit. Multimodals, right? So multimodals, we're just going to use the observed. But if I have skewed, I have some options. These would be the classic 3 options. I will say one more thing. If you go to Minitab and you say fit another distribution, it's going to give you a list of like 100 different distributions. on that list, I suspect none of you can explain 99% of what they are. Log, likelihood, the Johnson distribution, the blah, blah, blah distribution. No one has any idea what most of these things are, right? The big ones, exponential, Weibull, log normal, people know what these are that have had statistics classes. We will use those. If we don't fit those, we'll use just the observed and move on. But there are ways if it is skewed. Are we okay so far? All right. As a brief review, hopefully you've had some exposure to distributions. If you haven't, let's at least go through the Weibull. A Weibull distribution is very popular because it can fit a variety of distributions by changing the shape parameter. A normal distribution's parameters are mean and standard deviation. A Weibull's distribution are shape and scale. There's also a 3-parameter Weibull, but we'll do the 2 parameters. We have a shape and a scale. The shape is the important one. If you look at a shape of 1, that is a shape of 1. What distribution does that look like? Anybody? An exponential distribution is the special case of a Weibull where shape is 1. Exponential is a special case of the Weibull. The shape is 1. If your shape is less than 1, you come down the curve faster. If the shape is less than 1, you have a strictly decreasing curve. You just come down at a faster rate. If the shape is above 1, you will start to get a peak and a tail. You'll start to get a bend, or not strictly decreasing anymore. If I look, for example, at a shape of 2, what does a shape of 2 look like? That's skewed to the right. If you ever wonder how your professor makes a skewed right distribution, he just makes a Weibull the shape of 2. There's nothing tricky about that, right? Shape of 2 would be a skewed to the right. If the shape is 3.5, a Weibull basically is the same as a normal. When the shape gets to, say, 3.7, then you'll see a skew to the left. The nice thing about a Weibull is basically what the shape parameter is, you'll either get strictly decreasing, skewed right, skewed left, or normal. Therefore, if it fits a Weibull, if it fits a normal, it'll also fit a Weibull. If it fits an exponential, it'll also fit a Weibull. So Weibull becomes a general one. If you go to Minitab and you hit process capability non-normal, it defaults to Weibull. That's because it's the general fit distribution when there's a distribution fit. If it's, again, 4 modes, nothing's going to be very good fit. All right, how are we doing? We okay? For that reason, if you pick on the non-normal, we can select Weibull. Now, you could do distribution fit, and there is information in the appendix, and you could try to fit exponential, you could try to fit log normal to see which one ends up being a slightly better fit, or you can, if you have skewed distribution, just kind of default to the Weibull. Or pick best fit. If we do a Weibull, a couple things we notice. Minitab will give us shape and scale of the Weibull. It will give us a sample mean. Disappointing to me, it does not give me the standard deviation overall, but it doesn't. But we're given a mean, a shape, and a scale. It's going to calculate the observed. Does this number require the Weibull fit? Nope. It's just going to look at the which values are out versus the total sample size. This one right here is distribution free, or if you want a fancier term, use non-parametric. Non-parametric is a distribution free, no parameters to the model. It's going to come back and estimate a PPK. If you try to do this on your own, you're probably not going to do it unless you read a textbook of the actual formulas, because the formula that's going to use is a slightly different approach. I'm not going to spend a lot of time going there. If you want to do this by hand, you'd have to look up the formulas for it. Notice that there is no PP. The reason there is no PP is because one-sided specification. But in this case, if you assume a Weibull, you would get an expected PPM of 241,000. This is actually a reasonable difference between the two. But if you assumed a Weibull, that's what you would expect if you filled in the gap with more data. Some of you may remember that for many distributions, they require that x be greater than 0. Many distributions cannot be fit unless all the values are positive. If you run into the case where you have negative values, so if you have negative values, you may just want to add some constant to make them all positive. I'll say that in words. If I have negative values, I might just add everything to 100, and that will shift everything to all be positive values, assuming that everything is above 0 then. So just add some number to the data, if you have to make everything positive. But sometimes you fit a distribution, it says you have negative numbers, it can't fit that. That's how you get around that. Questions on that? All right, we covered a lot of things. It's worth it to make sure that we're clear on what is the most important things to remember. I will expect you to know the difference between these 4 indices. I will need to expect you to know whether or not you include the mean or which technique you are to estimate variation. I would expect you to look at these from a diagnostic standpoint and help identify mean off target, special causes, which would be out of control on an SPC, or high sigma within. High sigma within would be a fail CP. I want you to be appreciative of the fact that PP and CP are more about the potential. What would happen if you could shift to nominal? PP and CPK are much more closely aligned with parts per million because we're including the mean as well. We did this in class to help us with diagnostics. Usually a gap of, say, 0.5 of an index, so CP of 1 to a CP of 1.7. That's a pretty big difference. Try to be clear if I ever gave you a question like that. And then if you do have the case where your data is not normal, and particularly if it's skewed right, skewed left, you can use a Weibull or another distribution fit to make your estimate. If you have the multimodal case, best thing to do is typically just use the observed. You're not going to get a good distribution fit, or highly unlikely a distribution fit that you can reasonably explain to people for that. Just use the observed. I do give you how to do a distribution ID plot in the appendix, which you can go through that if you wanted to. All right, that's it for today. Thank you.